Our next speaker is a software engineer at NPM and represents the individual membership on the Node.js Foundation Board of Directors, and will be telling us about systems programming-inspired developer tools for JavaScript. Everyone make some noise for Ashley Williams.
Can everybody hear me? Yeah, okay, the mic is working. I broke it 3 times back there. Hi, I'm Ashley. The name of my talk today is Lucy in the Sky, Close to the Metal. How many people here have heard the phrase close to the metal? How many people know what it means? All right, well, then don't pay attention because that's kind of what this talk is about. With close to the metal, what it basically means is that the metal is nearby, and I've created a small graphic for you to understand that, where front-end development is space, and the metal is the computers. And so if you get anything from this talk, you can just gaze into those interesting backgrounds that I spent way too much time on. But basically, this talk is really going to be an introduction to some systems programming concepts for people who identify as front-end developers. So even if you're not necessarily a front-end developer, maybe you do back-end stuff, you'll get some stuff, but this is definitely focused on stuff for the front end. So as I was introduced, my name is Ashley Williams. You might know me as AG Dubs from the internet. If you follow me, I'm sorry. And if you're thinking about it, think long and hard about it. I work at this tiny little company that you may have heard of called NPM. And as Ken said, I also represent all y'all on the Node.js Board of Directors. So if you have questions about how sustainability works in open source and governance, I have a lot of opinions, so you can find me later and talk about those. So my favorite way to introduce myself, though, is that I really love programming languages, like a lot. And the way I like to say this is that I really like to think about thinking, especially the type of thinking that happens when people write code. And this isn't just like a cute way to sum myself up. I'm like seriously into this stuff, and we'll talk forever about it. So do note that while there are some practical takeaways from this talk, I really like coming at it from a theoretical point of view. So be open to that. So I have written a lot of Node, I've written Ruby, I've written Erlang, but recently I've been picking up a programming language called Rust. How many people here have heard of Rust? Okay, soon it will be all of you, because here it is on the screen. Rust is a systems programming language. This is how it describes it. And then it goes on to say that it runs blazingly fast, prevents seg faults, and guarantees thread safety. But if you don't know much about systems programming, that probably doesn't mean a lot to you. So we're going to focus on that very first one. So this talk, again, is about systems programming for front-end devs, and a lot of these things are things that I ended up learning through my introduction to Rust. So the very first question we have to ask ourselves is, what is systems programming? How many people in here already have a definition for it? They got it. All right, all right. No, I'm just kidding. Stick around, fight me over it. But definitions are always really tricky, and my favorite way to do definitions is to kind of bring up a dichotomy. So when we're thinking about systems programming, we can think about this binary between the idea of systems development and applications development. If you know me at all, you know I love philosophy, and I love the philosopher Jacques Derrida, who says that all binaries are false. So it turns out that this one is also false. But we're going to use it to kind of understand these definitions, at least a little bit. So in general, we can define application programmers as people who write software which provides services directly for users. So if you're writing an application, maybe you're writing a web application. The primary consumer of that web application is going to be somebody sitting at their computer, a human being. Systems programmers, on the other hand, tend to write software which provides services for other software. If you're already seeing how this dichotomy is breaking down, you're right there with me here. But in general, the idea is that they are providing software that's going to be working with other software. All right, so we can kind of see ourselves in development as having this one arrow here pointing towards users and the others to the computer. Now, you'll see I didn't split dev. And the whole point of this talk is that while we may focus on one type of programming, it's really important to have a perspective or some sort of circumspection of what the other type of programming is doing. I am a huge fan of interdisciplinary, holistic understanding, and so that's really what we're going to be talking about today. So in general, systems programmers can be a little bit defensive. They wouldn't like the idea that at any point, maybe I would suggest that application developers actually do a lot of systems programming. So they like to say, well, systems programming it requires a great deal of hardware awareness. They're kind of like, you know, we're actually close to the metal, and we're not sorry. But the interesting thing about that is if you think about particularly front-end development and how it's changed, particularly in the most recent times, you know, modern web development also requires a great deal of hardware awareness. Think of all of the devices that have to support web applications. Like, just across those different processors, you're looking at a lot of stuff, and you really have to pay attention to the hardware. So I like to say, you know, we're also kind of close to the metal. Or we're not exactly close to the metal, but we really have to think close to the metal. Because there's a lot of things that we need to think about. And when we often think about web application performance, we tend to focus very strongly on network performance. And so network performance tends to have to do with file size. There's a couple other things, but file size is a big one. We'll talk a little bit about file size today, but I really want to focus on these other two, which is going to be device performance and browser capabilities. And so with the idea that front-end developers really do actually have to think and be aware of hardware that their applications are running on, why don't we think of front-end development as systems programming? And so this is an interesting question, and the reason that I came up with is that because we have abstractions, and abstractions are really awesome. Abstractions are the thing that make us go a little bit further away from the metal. We abstract away from it. And JavaScript and the JavaScript ecosystem has tons of abstractions. So this wouldn't be a good computer science talk if I didn't quote Dijkstra, so let's do it. All right, so Dijkstra says, the effective exploitation of their powers of abstraction must be regarded as one of the most vital activities of a competent programmer. So right here, Dijkstra's saying, like, you program? That means you're abstracting. And when you are doing work, managing, creating abstractions, that's the most important part of your work as a programmer. So that's a pretty big deal. Now, this doesn't actually explain at all what abstraction is. But luckily, there's this awesome book called Types in Programming Languages, also known as TAPL. It's a big, big book, written by this guy, Benjamin C. Pierce. And he kind of defines it by calling it the abstraction principle. And he says, each significant piece of functionality in a program should be implemented in just one place in the source code. So from this definition, it kind of harkens this idea of dry, like don't repeat yourself. We abstract away stuff so that we don't have to put it all the same thing, all different places. We don't want to do that. And this definition's okay, but I am a real scientist, so I get my definitions from Wikipedia. And so Wikipedia says, abstraction tries to factor out details from a common pattern so that programmers can work close to the level of human thought, leaving out details which matter in practice, but are immaterial to the problem being solved. So I think that while keeping our code dry is a reasonable thing to do modularity with and do abstraction with, fundamentally, abstraction really is what we're doing so that we can actually solve interesting problems. We can abstract away some of the ones that are hard and really focus on the ones that we are trying to solve. And in particular, I think abstraction works really well because, and this is Abelson and Sussman, who wrote an amazing book, Structures and Interpretation of Computer Programs, and they say programs must be written for people to read and only incidentally for machines to execute. And I absolutely love this. And what's fun is that I give lots of programming talks, and I always use this quote, and I usually focus about the part about humans being able to read. But today, we are going to talk about that incidental issue of the machines needing to execute it. So we'll keep this in mind. All right, so abstractions are awesome. They let us write code so that other people writing that code can understand them. But it actually turns out that abstractions are extremely expensive. It turns out that being able to write code for humans and being able to write code for computers is a little bit at odds. So Nolan Lawson is someone who I think is really awesome. He wrote this amazing blog post called The Cost of Small Modules. And he kicks off this blog post by saying, the more I modularize my code, the bigger it gets. And this exposes a small bit of irony because we're like, oh, breaking up our code into tiny little pieces is like super great for readability and maintainability. But, ironically, it actually ends up making our code a lot larger. And in this paper, he actually says not only does it make it larger, but it makes it slower. And so the alternate title that he gave this paper was Why One Horse-Sized JavaScript Duck is Faster Than 100 Duck-Sized JavaScript Horses. And of course, I read this and I immediately was like, I gotta draw it. Gotta draw that immediately, for sure. But in this paper, what he does is accounting for the exact same bundle sizes. Depending on how you put your modules together, you could see a smaller or larger runtime cost. So again, we're not talking about latency on the network, large files. We're talking about literally on the metal. Depending on how you put those things together, it's going to change how quickly the program runs. And that has a lot to do with how the computer actually has to interpret and run the program. So Rich Harris, who's also a super awesome developer, I also love that he's not a professional web developer, he's a professional writer and just does it on the side, which is really great. He wrote this paper about, small modules, it's not quite that simple. And in it, I think he really articulates a point that I really like to make, which is, yes, small modules are easier to write. Yes, they're easier to test. These are all things that make your life as a library author easier. However, it turns out that this stuff that we do to make our lives easier comes at a significant cost for others. So I work at NPM, so I'm allowed to make these jokes. So if you've ever taken a look in your node modules folder, all right, I'm not talking about like, oh, we modularized some of our code. When you look at what NPM has been able to do, it's the largest package manager literally in the world. People are using modular code to an extent that we have really never, ever seen before. It's really, really big. And I'm here to say, yeah, these jokes happen, right? This one, I'm sure you've seen this one, all right? Yeah. So I'm here to say, that's actually friggin' awesome, because as I said before, abstraction makes code easier to write. We're able to solve the problems that really matter to us, all right? We can make it more easier to maintain. However, it does turn out that the gravity of that node modules directory we need to mitigate that. But we need to mitigate it in a way where we don't lose the amazing developer experience that the modularity of the JavaScript ecosystem gives us. So I'm now going to talk about a couple of concepts, and we're going to focus primarily on the idea of runtime performance. I think probably we've been talking a lot about, the network performance and file size. And I'll talk a little bit about file size, because it turns out there's a small amount of trade-off, actually, between runtime performance and file size. In fact, in some situations, I'm going to recommend that you make your files larger, right? It's ridiculous. So, and all of this is because it turns out that while abstraction's really awesome, it comes with a cost, which is often known as the abstraction tax. Now, I had actually never heard of this before, and it didn't really even occur to me until I had started learning Rust. And one of Rust's marketing techniques is to say, we have cost-free abstractions. And I saw that, and I was like, I really like abstractions. Abstractions are cool. But wait, OK, if you have cost-free ones, then that probably means that the ones I have do have a cost, and I just have no idea what it is. So I should probably figure out what that is. But it was really interesting, because this, just even like a marketing technique, made me think, wow, it made me really interrogate my understanding of programming. So, and the way Rust is able to have cost-free abstractions is it has an amazing thing called this compiler. If you've ever tried out Rust, and I'm going to encourage you to try out Rust, the compiler is really awesome. So what is a compiler? And before I even go into what is a compiler, is anybody here worried about the difference between a compiler and a transpiler? They're the friggin' same thing, okay? I don't know why we're friggin' talking about two different things. They're the same thing, so don't worry about it, all right? So a compiler is a computer software. You can tell I got the definition on Wikipedia, computer software. All right, a compiler is computer software that transforms computer code written in one programming language, called the source language, into another computer language, the target language. So really, all a compiler is a translator. It's really just a translator. And the reason this translator is super awesome, and I'm going to focus on a compiler today, is because developers, it turns out, have different needs than computers. And you may find some systems programmers who tell you that they are a computer. This is not true. They have absolutely different needs. And one of the amazing things that a compiler is going to afford you is it's going to allow you to write something as a human and then be able to translate it into something that a computer is going to like a lot more. So in this way, we can write code for developers, and then the compiler can write the code for the computers, because we are not computers. All right, so I have some great news for you. You may already be a winner, or you may already be using a compiler. You almost definitely are. All right, so a really classic one that has been very popular is Babel. People in here using Babel? Yeah. Support them, yo, they work so hard. Babel's really awesome for people who don't know. It's able to take ES6 code or ES whatever year it is, whatever you want to call ES. I'm fine with it. It can translate that into the ES5 code that's going to be able to be used on almost all of the modern browsers today. So what that's doing is modern browsers, they're computers, they really only understand one thing. Some people think that the new syntax in ES6 is better for developers. So again, we're making that trade-off of better for developers, then translate it into better for computers. So another one that you might be very familiar with is Webpack. How many people in here use Webpack? All right, awesome. So Webpack is dealing with that kind of node modules directory situation. And so what it's going to do is it's going to take all your modules dependencies, and then it's going to bundle them up in a way that you can use them in your browser, which is super cool. Now, later on, I'm going to be talking about a couple of tools that actually are responding to Webpack, because Webpack doesn't necessarily bundle things up as well for runtime performance. But it certainly does do it so that your browser can understand what the heck is going on. So the very first tool I'm going to talk about right now is the Closure compiler. You can probably guess that the Closure compiler is from Google, based on its logo. And the Closure compiler looks like this. So one of the nice things about all the tools I'll show you is they all have in-browser REPLs, so you can play around with them. So what we can see here on the one side is the source code. This is the target. And so we see I have a function called hello. It's going to just print an alert, hello, and the name that's passed in. And then it's called with the parameter new user. And so this is just the white space only. So yeah, of course, humans love white space. Computers, they just don't really care about it. And so this is how it's compiled. However, I can move it towards the advanced. And let's see, what would this turn into? One sad thing about compilers is they do take time. So here we go. So this is taking this program, which has a function, has that abstraction, and because it has all the data it needs, it's able to completely remove that abstraction and just give you the code that you would need, only the thing that would need to run. It's able to remove everything else. So let's talk a little bit about what's happening there. Oh, I have multiple versions of this open. Good job. All right, so what Closure compiler is able to do is first it can remove white space. It's also going to shorten names. Humans like long names. You should name your variables long names, descriptive names, please. Then it's also going to do a neat thing called dead code removal. We'll talk a little bit about this later, but basically dead code removal is you're able to figure out what parts of the code aren't going to run. Your code couldn't logically get to that, so why would you add that to your code? It's just going to remove that for you. And then finally, and we'll get to this a bit later, this neat thing called global inlining. But I'll talk about that in a second. So the next tool is Rollup. Rollup is actually a response to Webpack. And a super awesome thing about what Rollup is able to do is Rollup was able to introduce several new features that are now, because of their success, slowly getting integrated into Webpack. So you can benefit from people having used this. So I'm going to talk a little bit about the concepts before I show you the exact code that Rollup does, because they're a little bit more complicated. So Rollup does something called tree shaking, and it also does something called scope hoisting. You may remember that earlier I said dead code elimination. Tree shaking is just dead code elimination. It's the same. It's an implementation detail, so also if people get rowdy with you about what you call it, pay them no mind. So yeah, I was really excited to see that Patrick yesterday already introduced everyone to the concept of an AST, or an abstract syntax tree. But if you kind of forgot, I love to think about abstract syntax trees because I used to be really into diagramming sentences in middle school. Did anybody else like this? Okay, I did get the impression that I was in a small group of people. But basically, I kind of like tree shaking because it evokes this interesting metaphor where if you can understand your code instead of sentences, it's kind of this logical decision tree. And then if parts of it are dead, and you like dead leaves are like brown, crappy, and then you like shake the tree, like the dead ones fall off. That's kind of nice. So it's like it's a nature metaphor. But yeah, so that's basically what tree shaking is this idea that you can look at your abstraction text tree, figure out logically what parts you could never get to, and then just eliminate those. Now, for your own code, you might be thinking, if I write code and I could never logically get to it, then why the heck am I writing it? But again, remember that node module's black hole. You're probably including a lot of code in your application that you didn't write. And you're probably not using all of that code that you included. So this tool and these tools are going to allow you to get rid of that cruft so that you're only bundling code that you actually need. This way you only have to pay the tax for the stuff that you actually want. All right, so again, only bundle the code that you need. All right, so next thing to talk about is scope hoisting. So this one kind of has a tricky name. But I kind of like thinking of it as module inlining. And there's a typo on this that I'll get to in a second because I cannot spell this word for the life of me. But basically the idea of scope hoisting is that every module can share the same scope instead of being loaded dynamically from different scopes. So when we use modules, we're requiring them from different files, lots of different files. It turns out that there's a pretty large overhead for that. And maybe if we were writing it ourselves, we would probably just maybe write it as one big module. But even if we didn't, Rollup is going to be able to turn all of those multiple modules into just one big module. So all of that overhead of a dynamic module loader is something that you don't need anymore because it turns out that the computer doesn't care if things are multiple files. Humans love it. Computers, not so much. All right, so it's really great to throw everything in. It's aggressive inline. Right? Now you'll never forget it, this guy. All right? So let's take a little look at what Rollup does. Rollup by far has the best, I think, interface on the web. It's really nice. So what you can see here is we have a couple of modules. We have Maths.js, so I guess maybe whoever wrote it was British. Maths.js, and then I wrote a really terrible one called Letters.js, really terrible function there. But what you can see is this is what is compiled out. And what it's doing is it's taking a look at that entry module and figuring out what you use. So assume that these two things down here are your node modules directory, and here's your entry module. And so it's going to take a look at what you end up using, and then your bundle is going to reflect the stuff that you actually use. So one thing you can see here is in the maths module, we don't use the square function. All right, over here, we're not using it. So it doesn't actually get included in your bundle. But let's say I wanted to modify the cube function to use square. All right, and suddenly, because I'm using it, now it's in my bundle, which is super neat. So again, we can just get rid of that. All right, and then it goes away again, which is cool. All right. So back to the presentation, back to the wrong presentation. Too many tabs forever. All right, so as I was saying, it's actually kind of hard to look up information about what inlining is and why it actually is fast. Well, I thought it was hard because it turns out I was spelling it wrong, and I got an amazing thing here where Google's like, did you mean why inhaling makes programs fast? I did not mean that. But the reason inlining makes things fast and makes things faster is because it turns out that calling a function has a tax. It has an overhead. And it's because the computer has to do a whole lot of other things to account for something that's in a function when it would otherwise not need to do so. The fun thing about this is that processors and some of the stuff that does this work kind of under the hood, close to the metal, are also trying to optimize this at the same time. So while we're using tools that help us do more inlining, the processes are actually working to make it so that we don't need to do inlining so it's fast already. So it's interesting to be working on it from both sides. Optimizations are always changing. But at least for the moment, inlining stuff is definitely very useful. All right. Now, one of my favorite inlining stories has to do with one of my favorite engines, which is V8. It's good for you. This is the real logo. And so, if you already know this, do not shout it out. Do not ruin it, okay? I have a question for you. Code comments can affect the performance of your JavaScript, true or false? How many people think true? How many people think false? Okay, so you're both kind of right, but fundamentally, the answer is that it's actually true. V8 uses the number of characters in a function body to determine whether or not that function should be inlined. It needs to be 600 characters. If it's less, it's inlined. If it's greater, it's not inlined. And it turns out that comment characters count. So there's a small performance here. Now, what I want to say is a lot of the performance issues I'm talking about right now are micro optimizations. So don't go back to your development team and be like, I'm never writing comments again because Ashley said it makes my code slow. That's not what I'm saying at all right? I have my own feelings about code comments that we can talk about later. But yeah, again, I'm not saying, these are things that I find fascinating. And when you write code and you're able to think about kind of how it's working under the hood, you make certain different trade-offs, but it's also just kind of nice to know how that stuff works. So the last tool I want to talk about is prepack. And the reason I'm talking about this one last is, one, because it's the coolest, and two, because it is not ready for production yet. So you should probably just play with this one. But prepack does a bunch of really neat stuff. So the three things I'm going to talk about, and prepack does way more than this, is loop unrolling, constant propagation, and constant folding. And these are like the official names, but I'm going to have some really easy ways to talk about them first. So the first ones we're going to talk about are constant propagation and constant folding. So constant propagation is the process of substituting the values of known constants into expressions at compile time. And this works side by side with constant folding, which is recognizing and evaluating constant expressions at compile time rather than computing them at runtime. So we can take a look at an example of this, a really simple one. All right, so this has constant folding and constant propagation. And it's important that the folding happens first. So folding is going to recognize that variable A, B, and C do not change, so we do not need them to be variables, and we can just plug them into that add function right down there. Propagation then checks out that add function and says, oh, we know all of the numbers that we need to add up. So doing this computation is something we can literally do right now. We already have all the information we need. And so this code right here just turns into console log 29, which is pretty cool. All right, I'm not going to do the wrong one this time. Yes. All right, so the last thing that I'm going to talk about with prepack that I think is really neat is loop unrolling. All right, so loop unrolling is going to eliminate computational overhead by rewriting loops as a repeated sequence of similar independent statements. And to demonstrate this, I'm going to use that classic interview question, FizzBuzz. Now, the interesting thing about loop unrolling is this is the one I have to warn you. This one makes your file size larger, but it's significantly easier for the computer to do. So let's take a look. All right, so here's FizzBuzz. And so if you ever do an interview and you want to be like, I'm going to write the most performant version of this, you can just write this amazing version right here. Because that's what prepack decided was going to work. So again, it's finding all those constants, it's plugging them in, it's finding the expressions it can evaluate because it already knows everything it needs to know. And then it sees that loop and it goes, I already know all the things I need to do to get this done, and just completely unrolls it into this version. So here's the most efficient way to write this. I'm going to get tweets where people are like, actually, but whatever. All right. So fundamentally what prepack is doing is like, let's do all the computation at compile time. I mean, like not all the computation, because then you don't really have a program, but a lot of it. And it probably is true that you have a lot of computation that you can get done at compile time. And writing it like that would actually make the code harder to read and maintain. So writing it in the way that's friendly for people and then letting the computer handle it is like a way better strategy. So here are the links for all those REPLs that I just shared. But what I want to tell you is you don't actually have to know how all of these work to use them. You just have to kind of trust me and their authors that they do work. And hopefully I've convinced you at least a little bit that some of these tools are really neat and can save you some performance with your JavaScript application runtime. However, what I want to end with is a little inspiration, which is what if you learned how to think like a systems programmer? So I have a project that I work on with a bunch of other people, and it's called Intermezos, and it's a operating system written in Rust. But it's not trying to be the next Unix in any way, or Linux. It's just not going to be that. Instead, it's basically the goal is I'm going to write something, and while I write it, I'm going to write how I'm writing it, because exploring all this stuff is super fascinating, and it turns out that documentation for building operating systems is really bad, like really bad. And it's kind of neat, the story about how this happened, because I never thought I'd ever write an operating system. I already went through that. I mean, one thing that's also important is Intermezos, the goal is to introduce systems programming to people who are already experienced programmers, but from a completely different area. Literally, when I talk about it with my partner, who I work on with this, we say, JavaScript developers. This is an operating system, like it's how to learn how to write an operating system for JavaScript developers. And so this is my partner that I write it with, and it's a really cute dog. And this whole thing started because he was like, do you want to like stay in and like put on some comfy pants and do a kernel tutorial with me? And he was like, yes or no? And I was like, heck yeah, that sounds great. Let's do this. And I was like, yeah, let's get close to the metal. This will be awesome. And then I like kind of started having a huge panic attack. I was like, oh, wait, operating systems? Like, can I write that? I don't even know how to start. This is super scary. Like, should I even write an OS? Is that a question I should be asking myself? I was like really, really nervous. I'm an anxious eater, too, so I really relate to this. But yeah, and the reason is because systems developers and systems programmers are not the nicest group in general. This is a website called osdev.org, and this is the required knowledge section. And I'm not going to get all the way through it, but I'm going to tell you it's pretty silly, and it's also really stupid, and you shouldn't listen to it. They say that if you don't comply with their required knowledge, you will look silly, direct quote. It's a good thing that I've never worried about looking silly, because yeah. We went ahead and did it, and we were doing this based on a tutorial that was written by this awesome dude named Philip Opperman called Writing an OS in Rust, and then we kind of extended this tutorial to build it out into this thing that we now called Intermezos. And so I did it. Like, I straight up wrote an operating system. It was not easy, but it was also very fun, and I was really proud. This is my tweet where I announce is like, look at my little tiny small OS that I wrote. The only thing it does is like kind of weird glitch art, print something to the screen, because the first thing we wrote was a VGA driver. You can see I was doing a bunch of weird math back there, who knows. The fun thing about, and also the awful thing about systems programming, is when you mess up, the errors are bad. I actually live programmed when I was introducing this project last year at a Rust conference. I was live programming assembly, and I had told them, I was like, the errors are bad. And then I messed up in the live programming, and I was like, nah, see, the error's bad. It's really true. We figured it out, but that was really fun. So if you've ever seen any of my other talks before, I kind of have this like ideology where it's like, if you wish to computer from scratch, you must invent an operating system. And you maybe are getting the vibe, I'm like, you got to do this. You don't. You don't have to. But this is definitely a thing that I'm into. So, but yeah, you don't have to invent the universe. If you don't feel like inventing the universe, you certainly don't have to. But if you want to, you can. And I feel like sometimes we tell people who want to that they can't, and I don't like that. And I also kind of want to say you should, because it's going to bleed into different parts of your programming career, and you're going to find it really helpful. So I like to tell people that the metal is closer than you think. So in conclusion, systems programming is writing services to be consumed by a computer. And human readable code is not always the most performant code. Extensive modular code usage is very awesome for humans, but not great for computers. But compilers are a really cool way to let us write one thing for developers and then be able to translate that for a computer. And so knowing all of this, we have to get the fact that system programmers are generally grumpy gatekeepers, and we should absolutely pay them no mind. It's ridiculous. And to learn to think like a systems developer is super useful and fun and completely worthwhile for a front-end dev. I would argue more worthwhile than ever before, becoming more and more relevant. And so I'll leave you with this inspirational message. You know I'm going to change it, right? So shoot for the medal, and even if you miss, it'll be fun, and you'll learn stuff. Thanks.